Hello dear students. So we shall begin our lecture on convex sets and their properties, which is another topic of this first unit, convex sets and their properties. So here we will be dealing with the geometry of n-dimensional Euclidean spaces, okay, and their properties. So let us give a brief introduction about the geometry of the Euclidean spaces. So basically we shall generalize our ideas of geometry from the 2 and 3 dimensional spaces. Okay. Say for example, in the xy plane, if I have a straight line, say something like this, say suppose this is the straight line y equal to x, okay, then can I write this straight line as a set? Okay. So you see it's very easy to write this straight line as a set. It is the set of all those xy in E square which satisfy x equal to y, okay, or it is also written like this. It is the set of all those xy in E square which satisfy x minus y is equal to 0. Okay. So this straight line can be considered as a or regarded as a collection of points. Okay. So such type of figures or such set of points, okay, is called a point set. So any subset of the n-dimensional Euclidean space, okay, any subset of this e to the power n is called a point set, okay, is called point set. So this straight line is also a point set. It can be regarded as a set of points, okay. So similarly, if we consider the straight line, say ax plus by equal to c, okay, then this is also a straight line, or say ax plus by equal to d, this is a straight line, general equation of straight line. Then this can be represented as the set of all those xy in E square which satisfy ax plus by equal to d, okay. So it is the collection of all those points in E square which satisfy this, right. Similarly, if I talk about a circle, okay, the circle or any circle with say center, origin and radius a, okay, so we can denote it by this. Okay, let me just select one circle from here. Yeah, this one. Okay, so if we have a circle, we can actually denote it somewhat like this. Okay. Okay, so suppose this is the circle with center, origin and radius say a. Okay, so this point is a0 and this point is 0 0. So what is the equation of this circle? This circle has the equation x square plus y square is equal to a square, okay, and so we can represent this circle as a point set. It is the set of all those xy in E square which satisfy x square plus y square equal to a square, okay, or we can write it this way. It is the set of all those xy in E square that satisfy this distance mod of xy minus 0 0, okay, 0 0 equal to or square equal to a square. Okay, what is this mod? Mod is the distance, okay, mod of say xy or x1 y1 minus x2 y2, okay, it is the distance between these two. So how is the distance calculated? It's root over of x1 minus x2 square plus y1 minus y2 square, okay. So that is the Euclidean distance, right. So this is the set of all those points in the E square which are equidistant from a fixed point. For that fixed point is the center of the circle, okay. So circle is also a point set. It can be represented as a point set. Now if we talk about circular disc, okay, say a circular disc means the boundary of the circle together with the interior of the circle, okay, that is called circular disc. So we have something like this, say this one. So this circular disc, let us place it somewhere here, and so okay, so suppose this is the circular disc with the same radius, say a0 radius a, and center is the point 0 0. Okay, so this axis, let me draw this axis again. Okay, this is the axis, x axis, y axis. Okay, so suppose this one. Okay. Okay, so suppose this is the circular disc. So how do you write this circular disc? Circular disc. So we can write it as the set of all those xy in a square that satisfy x square plus y square is less than or equal to a square. Okay, this is the circular disc. Any point inside this circular disc will be at a lesser distance than a. Okay, the distance of any point inside this circular disc is actually less than or equal to a. Okay, for points on the circle it is exactly equal to a. For points inside, the distance is smaller. Okay, right. Similarly, the outside of the circular disc, the outside or the exterior, okay, the outside or the exterior portion of the circular disc, exterior of the circular disc will be, this is it is the set of all those xy in a square that satisfy x square plus y square is greater than or equal to a square. Okay, sorry, this will not be greater than or equal to, I have written outside. Okay, so if I write outside or on the boundary, then it is greater than or equal to. So any point outside the circle will have distance from the origin greater than a. Okay, so the outside region is represented by x square plus y square is greater than a square. Okay, so that's how we represent sets. Say suppose you want to represent the right half plane created by this straight line x equal to 1. Okay, right half plane created by this straight line x equal to, so this side. Okay, this side. So how do you represent? This is the right half plane created by the straight line x equal to 1. Okay, so what is that? This is xy, set of all those xy in E square which satisfy this x is greater than or equal to 1. Okay, in this region the value of x is greater than or equal to 1. Okay, if it is left half, then it will be less than or equal to 1. Okay, so if it is the open right half, then equality will not be there. Okay, so this is actually called closed right half, right? Okay, so similar to that, if we come to the three-dimensional space also, if we have a sphere, say if we have a sphere of this one. Okay, if we have a sphere, then suppose this is the sphere, and I want to write it as a point set. Okay, so this is a sphere. So how do I write it? It is the set of all those x, y, z in R E square that satisfy x square plus y square plus z square is equal to a square. Okay, the spherical surface. Okay, surface of the sphere actually. Yeah, means sphere means we talk about the surface. Okay, so if we say the interior, the solid sphere. Okay, if we say the solid sphere will be S equal to set of all those x, y, z inside E. This is E cube. Okay, three-dimensional space. So x square plus y square plus z square is less than or equal to s square. Okay, in that case, this is the solid sphere. Okay, of course, this is the sphere with center, origin, and radius. Center is the origin. Okay, 0 0 0, and the radius is actually a. Yeah, this is the sphere with center, origin, and radius a, that can be represented this way. Okay, similarly, so if we have a sphere with center, say u, v, w, and radius a. Okay, radius a. So how do I write it? We will write it this way: set of all those x, y, z in E cube that satisfy this x minus u whole square plus y minus v whole square plus z minus w whole square equal to a square. Okay, sphere with center u v w and radius a. Okay, we can denote it by another notation, that is xyz in e cube, that satisfy this distance. We can use the distance between xyz and this u v w. Okay, this distance is equal to a. Okay, right, it is the set of all those whose distance is equal to a. Okay, distance from a fixed point is equal to a. Okay, so that way we can represent a sphere in e cube. Okay, so next let us try to see, or let us try to recall what is the equation of a straight line in e cube passing through 2 points. Equation of a straight line passing through 2 points. Passing through 2 points. 2 points, say I write it as x1. Yeah, let us write it as x1, x2. I have a special intention for this. Equation of a straight line passing through 2 points, x1, x2, comma y1, y2. Okay, so let us write it this way. So how do you represent this equation? Or okay, let us use the original form only. We'll just change it afterwards. Okay, so for passing through 2 points, x1, y1 and x2, y2. Okay, so we know this equation is y minus y1 by y2 minus y1 equal to x minus x1 by x2 minus x1. Okay, this is the equation, right? Now I can write it in a parametric form also, that this is the Cartesian form, right? So in order to write it as in a parametric form, I'll denote this ratio by a parameter tree. So any point on the straight line, actually any point xy on the straight line satisfies this ratio actually, right? That is the thing. So this by this equal to this by this should be equal to t. Okay, so they should be in the same ratio. Okay, so let's say this I write it as t. Okay, equal to t, say, then any point, then y minus y1 will be equal to t into y2 minus y1, right? And x minus x1 will be equal to t into x2 minus x1. Okay, right? So if I just use something like this, so from here I write y1 equal to y equal to y1 into 1 minus t plus y2. Okay, and from here I write x equal to x1 into 1 minus t plus tx2. Okay, sorry, here also it's ty2. Okay, so okay, I'll write it this way. I write the scalar first, y minus 1 minus t into y1 plus ty2, and here also x is 1 minus t into x1 plus tx2. Okay, so I write it this way. So this is the parametric form of the straight line. So where t can be any real number, right? So if t is 0, in particular we'll get y equal to y1 and x equal to x1. So x1, y1 is also a point on the straight line, right? Okay, so similarly when t equal to 1, it's actually y minus y1 equal to y2 minus y1. So y equal to y2, it gives t equal to 1 will give the point x2, y2. Okay, and in fact any real number between 1 and 0 will give a point between x1, y1 and x2, y2. Okay, you can try. So that is actually the section formula that you have done in school. So any point between these two points, okay, any point on the line between these 2 points can be written as this 1 minus t into y1 plus t into y2, where t lies between 0 and 1. Okay, so here what I have done, I have written I have got the parametric equation of the straight line. So that means what, any point on this straight line can be written in this form. Okay, so let us write that. So any point on the line joining x1 y1 and x2 y2 can be written as, okay, written as xy equal to, so you see 1 minus t into x1 plus t x2, okay, comma, and this one will be 1 minus t into y1 plus t y2. So if I use the property of that scalar multiplication and vector addition, using that I can write it as 1 minus t into x1 comma y1 plus t into x2 y2. Okay, so any point xy on the line joining these 2 points, okay, can be written as 1 minus t into x1 y1 plus t into x2 y2. Okay, where t belongs to real number, right? Okay, and correspondingly if we have any point of this type, then obviously it's a point on this straight line, okay, because it will satisfy this particular ratio. Okay, right, any point xy will lie on the straight line if these two ratios are equal. Okay, that is the thing. Okay, so we can generalize this concept. Okay, for the case of here also, the 3-dimensional case also, the equation of line passing through these 2 points x1 y1 z1 and x2 y2 z2. Okay, y2 z2, equation of line passing through these points is actually given by x minus x1 by x2 minus x1, x2 minus x1 equal to y minus y1 by y2 minus y1, right, equal to z minus z1 by z2 minus z1. Okay, this is the equation of straight line in this 3-dimensional space. So if I write this as t, then any point on that straight line also will be like 1 minus t into x1 y1 z1 plus t into x2 y2 z2. Okay, right, any point on that can be written like this. So using this idea, actually we will try to generalize the concept of straight line. Okay, so up to 3 dimensions we know how the straight line looks like. Okay, after 3 dimension it's just a generalization. It's a sort of algebra more than geometry. Okay, the concept is carried forward from geometry. Okay, and then we define it algebraically in Euclidean n-dimensional space. Okay, so first definition that will come, it's a line, straight line. Okay, straight line, what do we mean by a straight line in Euclidean space? Okay, straight line in n-dimensional Euclidean space. Okay, so you see whatever I have written here, if I denote this by a point, say x, okay, and I denote this by a point y, okay, then the straight line equation of straight line, or the set of points 1 minus t into x plus t into y such that t belongs to R. Okay, the collection of this type of points is actually the straight line, the given straight line. Okay, which passes through the points x and y. Okay, so this is exactly what we will write here. So let the straight line joining 2 points, okay, joining 2 points x equal to, so here I am using the coordinates as x1 x2 up to xn, and this point I am using it as y1 y2 up to yn. Okay, the straight line joining 2 points x equal to x1 x2 xn and y equal to y1 y2 or yn in e to the power n is the point set. Okay, the point set, say L equal to It is the collection of all 1 minus tx, or okay, one thing we can do, instead of writing this as 1 minus tx plus ty, we can also write it the other way. If I take some say, if I denote it by 1 minus t by lambda, then your t will be equal to 1 minus lambda. Okay, so I can write it equivalently. I can write it as lambda x plus 1 minus lambda y. Okay, where lambda is also in real number. Okay, so equivalently we can write it this way. So for the definition purpose, we will use that. So is the point set lambda x plus 1 minus lambda y, okay, such that lambda belongs to real number, okay, and a collection of all those points, okay, where lambda is a real number, okay. So in particular, if you take lambda equal to 0, then you get the point y. If you take lambda equal to 1, then you get the point x, okay. So straight line joining these 2 points in e to the power n is the point set lambda x. So this is actually a linear combination of 2 points x and y, okay, but a particular, means it's not a general linear combination, it's a particular linear combination where one scalar, where the sum of 2 scalars is actually 1, okay, sum of the 2 scalar coefficients, this is 1, right. So this is called a straight line in e to the power n, right, okay. So this one. So similarly, straight line segment, okay, if we have a straight line segment, so how do we denote by this? Okay, straight line segment in e to the power n, okay. So how it is denoted? The straight line, or the line segment, just I can write the line segment joining the points x equal to x1, x2 up to xn, and y equal to y1, y2 up to yn in e to the power n, okay, is the point set, say L equal to the set of all lambda x plus 1 minus lambda times of y, such that 0 less than or equal to lambda less than or equal to 1, okay. So if we restrict the scalar to be lying between 0 and 1, in that case we get the line segment joining 2 points, okay. So only this portion we get, okay, we do not get this, this, okay. So but if we have no restriction on the scalar lambda, in that case we get the straight line joining the points, okay. So line segment is different, it's a part of the straight line between two fixed points, okay, right. So this is the definition of line segment, okay. Then we have something called what is the distance between 2 points? Distance between 2 points, so I think I had given you this definition once. So distance between 2 points x equal to x1, x2 up to xn, and y equal to y1, y2 up to yn in e to the power n is mod of x minus y, okay. So mod of x minus y, so which is equal to root over of x1 minus y1 square plus x2 minus y2 square, okay, plus dot plus xn minus yn square, okay, this distance, okay, this is the distance between 2 points, okay. So I had given you the idea of circle. So circle in E square, it is denoted by the set of all those xy, which so let me write it in a different way. It is the set of all those x in E square, so where this x is actually x1, x2, okay, such that the distance between x and say x naught, x naught is another means the fixed point, okay, is exactly equal to a, okay, right. So this is the definition of circle in E square, okay. So we will generalize the definition of circle and sphere to get something called hypersphere, okay, hypersphere, Achha, before hypersphere we have something called hyperplane also. Hyperplane. Okay, just let us do that first. So for hyperplane, hyperplane is the generalization of this straight line, planes, etc. Okay, so straight line is given by ax plus by equal to some constant, say d. Okay, so here also in a hyperplane we will generalize this, means it basically represents a linear equation in x1 x2 up to xn. Okay, so yeah, so a hyperplane in e to the power n is is the set of points which satisfy this particular property. Okay, hyperplane in e to the power n is the point set this h equal to the set of this x1 x2 up to xn in e to the power n, such that c1 x1 plus c2 x2 plus dot 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 up to cn xn, this is equal to some quantity z. Okay, right, so that is called a hyperplane. So is the point set this for some fixed values, of of c1 c2 up to cn and z. Okay, so here the coefficients are fixed, right, the coefficients are fixed, and this constant term is also fixed. Okay, so a hyperplane in e to the power n is the set of all points x1 x2 up to xn in e to the power n which satisfy this. Okay, so we can write it this way. In short we write a hyperplane as h equal to, so we write it this way: set of x belongs to e to the power n such that cx equal to z, where c is equal to this vector c1 c2 up to cn. Okay, and x equal to x1 x2 up to xn. Okay, so this cx is actually their product. Okay, so taken x equal to this as a column vector. Okay, x equal to this taken as a column vector. So in that case we can multiply, so it's just matrix multiplication. Okay, so it's something like c1 c2 up to cn multiplied with x1 x2 up to xn. Okay, so this x in e to the power n is represented as a column vector, so in that case we can multiply this, okay, this row into this column, so it's actually c1 x1 plus c2 x2, okay, plus up to cn xn. Okay, so right, so equal to z. Okay, so here what we have defined for some fixed values of c1 c2 cn and z in R. Okay, so these are scalars, c1 c2 cn and z, they are actually scalars. Okay, or means real numbers. Okay, right, so we have something like this. So this is called the hyperplane. Okay, right, then we have something like, so just like a straight line divides a plane into two parts, right? If you have a straight line, it will divide the plane into this right half, left half, okay, and the part that is itself. Okay, so that way the hyperplane also divides the En into 3 parts. Okay, so the hyperplane Cx equal to z divides e to the power n into 3 mutually disjoint sets. Okay, mutually disjoint sets, which are, say, I write this as the half spaces. Okay, mutually disjoint sets, let's say H1 equal to the set of x in e to the power n which satisfy Cx is strictly greater than z. Okay, H2 is the set of all those x in e to the power n which satisfy Cx is exactly equal to z. Okay, so this is nothing but the hyperplane itself. This is the hyperplane itself. Okay, hyperplane itself. And H3 is the set of all those x in e to the power n which satisfy Cx is strictly less than z. Okay, so these are called this H1 and H3 are called open half spaces. Okay, so the first one, H1, is called right open half space. Okay, are called right. So let me write that also. Right open half space or just are called open half spaces. Okay, so H1 is the right open half space and H3 is the left open half space. Okay, so are called open half spaces. Spaces or planes actually. Okay, so open half spaces, right and left. Okay, so and if we have something like this also points sets of the type say a equal to set of all those x in e to the power n such that Cx is greater than or equal to z. Okay, are called, or b equal to set of all those x in e to the power n such that Cx is less than or equal to z. Okay, are called closed half spaces. Okay, closed half spaces, right? So right half space, open half spaces, closed half spaces we have discussed. Okay, right. So next is we can call what is or we can define what is called a hypersphere. Okay, so we generalize the concept of circle and that is called spheres. So how do you define a hypersphere? The set or the point set h equal to, or say x equal to set of all those x in e to the power n which satisfy x distance between x and a is equal to, say, epsilon. Okay, or say equal to r. R is called a hypersphere. It's called a hypersphere with center a, center a and radius r. Okay, so the concept is from the concept of circle and sphere, circle in 2 dimension and sphere in 3 dimension. Okay, so that concept. So we have generalized this here, the set of all those x in e to the power n which satisfy mod of x minus a equal to r. So what is this mod actually? This actually represents root over of x1 minus a1 square, okay, a1 a2 an, these are the coordinates, okay, x2 minus a2 square. Okay, so let us write this as part of the definition also. In exam also you can write, where x equal to x1 x2 up to xn, a equal to a1 a2 up to an is fixed, okay, this where x equal to this, a equal to this is fixed actually, a is fixed, and r greater than 0 is also fixed, okay, right. And mod of x minus a is actually square root of x1 minus a1 whole square plus x2 minus a2 whole square, okay, plus dot 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 up to xn minus an whole square, okay. This is the complete definition of a hypersphere, okay. So in E3 or E2, a hypersphere is actually a hypersphere is a that is a circle, okay. In E2, hypersphere is a circle. In E3, hypersphere is actually a sphere, okay. Hypersphere is a sphere, okay. In E3 it is a sphere, right. Okay, so what is an epsilon neighborhood of a point? Epsilon neighborhood. Okay, so in our real analysis we had done what is an epsilon neighborhood of a point. It is the set of all those points x which satisfy mod of x minus a less than epsilon, okay, this one. So here also it is something similar, because we already have the definition of this mod, okay. So what is that? Epsilon neighborhood of a point, and an epsilon neighborhood of a point a in e to the power n is the set say n equal to, or n epsilon equal to, the set of all those x in e to the power n which satisfy mod of x minus a is strictly less than epsilon, okay. So it's the set of all points which lie inside the hypersphere, okay. That is, it is the set of all points that lie inside the hypersphere, hypersphere mod of x minus a equal to epsilon, okay. So the set of all points which lie inside the hypersphere mod of x minus a equal to epsilon, okay, is called epsilon neighborhood, okay. So an epsilon neighborhood of over the point is defined with a set of points which lie inside the hypersphere with radius center a and radius epsilon, okay, right. Okay, so a point a is said to be interior point of the set x if there is an epsilon neighborhood about a that contains only points of the set x, okay. Then we have also have boundary point, then closed set, open set, okay. So these things also we will just write, and then we will go to the idea of convex sets, okay. So for the time being you study up to this, we will continue in the next lecture.